In earlier lectures, we looked at some rules involving exponents that were whole numbers. Today we're going to look at some rules involving exponents that are fractions and how do we interpret a fraction exponent. So typically the way that we deal with this is if we have something like x to the 1/2, the way we interpret this is really just the square root of x. So you can see that the fractional exponents have a little bit different way of interpretation. Likewise, something like this, if you see x to the 1/3, you can interpret this as the cubed root of x, and etc. X to the 1/4, this is the 4th root of x. And we can go back and forth. I can write it from this form back to this form, or starting with the left and going to the right. So because of this, I can actually make this a little more complicated too, not just have the 1 over a number, which we usually think of as the root, the radical of that. So 1 over 2 is the squared root, 1 over 3 the cubed root, 1 over 4 the 4th root. I can actually make fractions that are a little more complex, something like this, x to the 3/2, for example. But we can still use our exponent rules from previous lectures to figure out what exactly this means. So the rule doesn't actually change. I can actually take this particular expression and break it up into x to the 1/2 all raised to the 3rd power. Because if you remember our rules, our exponent rules from earlier, if you have something to a power and then that's raised to another power, you just multiply the two numbers together. So this is an equivalent statement as this, because 3 times 1/2 is just 3/2. So then if I want to go further with this, I could say, well, x to the 1/2, this is really just the square root of x, and then all of that needs to be cubed. So I can get an expression that looks like this. So this is a way of writing it in the radical form. Now I also could have gone a different direction, because 1/2 times 3 is 3/2, but I could have left the 3 on the inside and the 1/2 on the outside. For example, this. I could have rewritten this statement as x to the 3rd power and then all of that raised to the 1/2 power. Again, this is okay because if we multiply these two exponents together, we'll get back to 3/2, which is what we started with. So this is an equivalent statement. But then this would mean that I should take x cubed, and then that entire statement I should take the square root of x cubed. And we actually get two statements that look a little different, but in fact they're equivalent. Both of these mean the same thing. You can go in either order. Now the reason this is important to be able to go in either order is because sometimes going one order will make solving a problem easier than going the other direction. I'll show you an example. So let's take something like this, 8 to the 4/3 power. Well, according to what I just said, I could break this up two different ways. I could either think of this as 8 to the 4th power, and then the cubed root of that, so the cubed root of 8 to the 4th. Or I could think of this as the cubed root of 8 first, and then take all of that to the 4th power. Now, if you think about the order of this bottom one is actually a little easier, because 8 to the 4th, that's not really a common one that we might just know off the top of our head. And plus, it's a really large number. So here we'll take 8 to the 4th and get a really large number, and then have to try to take the cubed root of that. If we don't have a calculator, that could take a lot of time. So this way is actually maybe not the best way to go. But if I look here, well, I know what 8 to the 1/3 power is, because 8 to the 1/3 just means the cubed root of 8. So I know that that's actually just 2. The cubed root of 8 is 2. And then I can take the 4th power of that, and I'll find out that this is equal to 16. So really the way that I can interpret 8 to the 4/3 power is just 16. That's the number that it reduces to. Now you would have still gotten the answer if you had gone this way, but again, the problem is that you'd be dealing with a lot bigger numbers, and if you didn't have a calculator, it might take you a lot more time to figure out what that value is. So let's look at another one. So something like this, 16 to the 3/2 power, will run into the same situation. If I break this up the two different ways, I could really think of this as 16 cubed and all of that raised to the 1/2 power, because 3 times 1/2 will be 3/2. Or I could think of this as 16 to the 1/2 power, or the square root of 16, and then all of that cubed. Again, I run into the same situation. I have no idea what 16 cubed is. I could figure it out, but then it's a really large number, and then trying to take the square root of that really large number, it might be really difficult. So if we're working by hand, we probably don't want to go this route. But this way is a lot easier. I know what the square root of 16 is. It's 4. And then if I take 4 to the 3rd power, that's a relatively common one. So I found out that this expression is equal to 64. Again, if you went through this process, you would still get 64, but it might be a little more difficult. So this is why it's good to be able to break these up in several different ways. Now, likewise, we could go from the radical expression back to the fractional expression if we wanted to. So not necessarily with the constants, because in this case we're just trying to simplify constants, but sometimes it's a good skill to be able to go from something like this back to the exponent form, because the reason is we don't really know how to do a whole lot of things with radicals as far as arithmetic, but we know a ton of things about exponents because we have an entire section that's just all about exponent rules. So if I can take this and then convert it back into the exponent form, then this might help me solve some problems. So for example, here I know this is x to the 4th and then the cubed root of all of that. So it's x to the 4th and then all of this raised to the 1/3 power. Well, my exponent rules tell me if I have something raised to a power raised to another power, just multiply these two together. So this is really x to the 4/3. This is the way I would write this as an exponent form. Now, why is this important? Well, if I gave you an expression like this, and asked you to simplify this, again, we don't know a whole lot about radicals. I don't really know how to simplify a cubed root with a square root. That doesn't really make much sense to me. But if I can convert these into exponential expressions, I know a lot about exponents. I know how to deal with the rules of exponents, especially when we're dealing with the same base. So here, this is really x squared, and then the cubed root of x squared, so x squared to the 1/3 power. This one is just the square root of x, so that's just going to be x to the 1/2 power. X squared to the 1/3, I'm just going to multiply the exponents, so this will be x to the 2/3 power. And we'll leave this one here as x to the 1/2. Now my exponent rules tell me if I have x times x, and they're both raised to powers, since these are the exact same base, I can just add the exponents together. So really this should equal x to the 2/3 plus 1/2. And then we can combine these fractions. So this would really be 4/6 if I want to create a common denominator, and then 3/6 right here. So I could rewrite this as one single expression, x to the 7/6 power. So that would be probably a better form to write this in, because it's just a lot simpler and a lot easier to look at. And of course, if I wanted to, I could continue to rewrite this as a radical expression. This is really just x to the 7th power raised to the 1/6, so the 6th root of x to the 7th power.